My name's Amanda Lynch. I'm an atmospheric scientist here at IBES, among many other things, but that's the quickest way to say it. And so what I wanted to talk to you today was about some work that I've been doing for the past few years with a group in Norway, represented today by Brick Dale and several other people who were involved. And I just wanted to give you a kind of a sample of the kind of thinking that we've been doing in this project and a particular conundrum that I've been wrestling with in this. So one of the things that we understand is that the Arctic is changing into a place that we humans have not experienced before, although the Arctic has been ice-free in recorded history. And so the ice is retreating and charismatic megafauna such as polar bears are having trouble following it north. However, it is creating pathways for other species such as humans. But we know that this is a system that has some tipping points in it. Every cryospheric system has tipping points because of the freezing point of water. And so we need to understand where the tipping points might be in this system: physical, chemical, biological, social. So at the moment, the Arctic nations are jockeying for position. There is a lot of geopolitical tensions rising in the region. There's fisheries here, there is tourism, there is freight, but what's got everyone's attention are the oil and the minerals. So there are billions of barrels of oil, there are trillions of cubic feet of natural gas, there's copper, gold, iron, you name it, all in this largely untapped region. At the same time, we have political challenges. So, for example, Russia has recently requested in 2017 to declare this central Arctic zone to be international waters. And that's not because they don't want to claim it, it's because they want to cut Canada out of any deals. The Danes are opposing that because they think they're in a strong position because they have a claim to Greenland. The Chinese and Australia are trying to work with Greenland to mine rare earth metals so that Greenland can finance its bid for self-determination, which in turn is going to influence the Danish position. So it's an extremely messy context. And so what I want to talk about today is just one small element of that context, which is shipping, because all of these elements have challenges to them that are different. So what's involved in shipping? Well, there are a whole lot of issues that you have to understand. It's not just whether the ice is retreated and the ships can go through it. We need to understand that question of sovereignty. Who is claiming which waters in the Arctic Ocean at the moment? And are they requiring tolls and permits to sail through those waters? Are they charging tariffs for the use of their facilities? Who is the crew on these ships? You know, if you have a highly experienced Filipino tanker captain who has never gone through the Arctic before, that captain is not going to be very keen to pilot his or her way through this particular environment. What does the insurance say, and how is your particular ship rated? Do you require an icebreaker escort? Do you require 2 icebreaker escorts? Where are you going to get them from? The Russians have most of the icebreakers, the Canadians have a few, the Americans have 1 or 2, but really the icebreaker game is a Russian game. Where are the deep water ports? The US in particular has very few deep water ports that are accessible to the North Water Passage or to the Northern Sea route, and so again, dealing with these international ports, you can get some things in at Tuktoyaktuk, but mostly you have to get out through the Bering Strait in order to take advantage of the ports. And then, of course, there's the question of commodity prices. It's It is a shorter route to go through the Arctic than it is to go via the Suez Canal, but the ships have to sail more slowly and they often need to employ icebreakers. And so it's not necessarily a cheaper proposition to take the shorter route in this case. And so what's the value of the cargo you're carrying, and is that going to have an influence? And then, of course, there's the ice. The ice is retreating, but it's still there. And the ice is still very dangerous. So even if what you're left with is mostly open water and icebergs, you really don't have a situation, think Titanic, where you're absolutely safe. And so what we need with this is we need excellent forecasters, we need really good observations, usually based on synthetic aperture radar, but we also need to understand better how to do ice forecasting in a system that we've really never experienced before, that's undergoing changes that often make no sense. And so it's a really unique challenge to be able to make this a safe proposition even before you decide, you know, is it economically worth it? Is it socially appropriate? Is it environmentally sustainable? All of those questions are moot if it turns out we can't even do it. And so I am working on one part of this forecasting problem, which is about the polar vortex. You've probably all heard about the polar vortex. It either ruined your winter or it made your ski vacation a few winters back. The polar vortex is over the pole. It's a circulation that's trapped over the pole that's a necessary component of the global atmospheric circulation. And within it are embedded waves that help to steer and determine the weather systems that go around the globe here in the Northern Hemisphere. And so it's really understanding the polar vortex and being able to generate simulations of it that can guide forecasting that is a part of the problem that we've been looking at. So this is the hypothesis that's been proposed in the literature. The hypothesis is that if you have enhanced Arctic warming, because we have the snow albedo feedback effect, and so it's warming faster in the Arctic than it is in the equator, and therefore the equator to pole temperature gradient is getting less because the equator is warming up more and the poles are warming up more and the equator is warming up less. So if we have a decreased equator to pole temperature gradient, what that will do is weaken the mid-latitude jet stream just through a simple dynamical balance. What has been suggested in the literature, and actually I want to take that tick off because I'm starting to doubt this one, is that if you have a weaker mid-latitude jet stream, you should get a slower eastward progression of planetary waves. It's the planetary scale waves that carry the weather systems that the forecasters are seeking to forecast. However, some evidence is emerging that maybe you can't actually make this step, and I'm still thinking about that one. The last part, the part that got everyone excited in the literature and there are many, a flurry of publications on this, was that what you would get then is higher wave amplitudes, and that's what we're seeing when we talk about the polar vortex, you know, being here in Rhode Island or, you know, anywhere else in Europe in the mid-latitudes, is because if the waves are really big, then polar air can be sucked down into the mid-latitudes and we get these frigid situations here. By the same token, you get warm tropical air being sucked up to places like Alaska where it gets much warmer all of a sudden. However, this is a very hand-waving argument at the moment, and so I wanted to put some real dynamics into this. And so we took a theoretical approach, and we also used a pile of different new data sets that were available to see if we could actually determine what the wave amplitudes were rather than just kind of say, oh, you know, it's like surf on a beach and, you know, something like that. So, so we calculated the wave amplitudes. And this is what we found. We had a data set that was, it was a really great data set. It goes from 1860 up to the present day. And the interesting thing about this calculating the planetary waves is, of course, when you've got a large amount of data, this is 6-hourly data for over a century, we can calculate not just what the average wave amplitude is, but the distribution of the waves in any particular year. And so we can see, you know, the lowest amplitude waves and the highest amplitude waves, and then we have the median here. And so you can see it's kind of, it's roughly a normal distribution, except for down here near the beginning where it seems to be, you know, it's getting so zonal. It's you know, you can't have a negative wave amplitude, and so it tends to be capped at that point. So what are we seeing here then? Is the wave amplitude increasing? Well, it is increasing here, but then it stops around 1940 and it's been flat since then. And so the question is, why has it been flat since then? And so that was the question we had to answer. So clearly the simple progression that's being argued in the literature, that's not there. But there's something going on, and it's something to do with this stabilisation. And so what we looked at was the pole to equator temperature difference to see if, you know, that there was that link there. And we saw that yes, the pole to equator temperature difference is decreasing exactly as everyone predicted. You know, you can see that, and it's actually, you know, statistically significant. We're seeing the decrease. That's all well and good. But what really interested me was how the distribution of temperature changed. So what we're finding is the pole to equator temperature difference is decreasing, but there's a limit to how low it can get. And that limit is because of the freezing and melting point of water. So while there is still ice in the Arctic, there's a limit to how warm the Arctic Ocean region can get. And if there's a limit to how warm it can get, there's a limit to how small the pole to equator temperature gradient can get. And so what we're finding is that while there's still ice, there's a limit to how much you can push this system. So this is one of these non-linearities brought about by the freezing point. And so what that means then is that the ice in the Arctic is holding this whole set of changes at bay, perhaps. And so if all the ice goes, will this suddenly accelerate? The likely answer to that is yes, but we don't, because we don't understand enough about how this system is reacting, we don't know. So what? So the reason we care, as I said, is that if this is occurring, then increased extreme weather events where many people live, large swings in weather from one day to the next, and a reduced ability to anticipate system behaviour on decision-relevant timescales. And so those are the things that we're trying to come to grips with as we're thinking about, you know, what's going on with these waves. Are they really behaving in this way that's been hypothesised in the literature? And so what we find then in this situation is that we're needing to think about a balance between very fast changing things and very slow changing things. And so again, this is a question of scale, a question of temporal scale rather than spatial scale, where in the short term we have a passion for economic development, a quest for self-determination by the Greenlanders and many other Indigenous peoples in the Arctic. We have the question of energy and where are we going to where are we going to get our energy from? There are complicated questions about who has the authority to make decisions in the Arctic. And all of this is happening in the context of extreme weather that we don't quite understand and we haven't got a handle on yet, except that we think that the sea ice is actually holding the system together at the moment. On the slow side, we have this long, slow changes in climate that seem to be accelerating, and associated with that is going to be the loss of snow and ice. We have the question of polar flora and fauna, and when we lose a unique environment, what happens to those unique living creatures, and are we going to be able to create refugia for them? There's the question of subsistence and culture and the peoples who have lived and worked and experienced the Arctic for many generations and the values that we put on that. And then finally, this question of sovereignty, which is fraught. And so the question that we're left with is, when the ice disappears, will we suddenly have a huge blow up of extreme weather? And that ultimately is the question that we're trying to answer. But I would need another 5 minutes to go into that, so I'll stop there.